Hi, welcome to this module. So this is a continuation of our previous few modules on sensors, right. So we have seen several type of sensors till now, including our heater, and then you have interdigital electrodes on the heater. Then you have seen that how the sensor can be used to measure the impedance change of the cells, right, or of the tissues. Then you have seen how we can measure the change in the mechanical property, the elasticity of a material with the help of a piezoresistive microcantilever, right. And then we also looked at how we can design a drug screening tool to identify a drug for particular patients, or in another way a patient centric platform. We have also seen that the sensors can be used to understand the antibiotic susceptibility testing, which antibiotic will be effective to that particular bacteria. Now let us see microfluidic chip that can be used to understand angiogenesis and anti-angiogenesis properties. So now what exactly angiogenesis means, and what are the different combination of therapies that one can use to understand that how we can stop the angiogenesis. Okay. So angiogenesis is the growing of blood vessels, and in a way that when there is a cancer, right, then the nutrition, see, cancer is what, it is a similar cell of our body, just notorious one, no. If you know, if you are more notorious, you require more energy. If you are less notorious, calm, sitting on the same place, you require less energy. So notorious cells requires more energy. If we stop energy to the notorious cells, what will happen? Cells would die, right. So cancer are notorious cells, and the best source of energy for our body is carbohydrates. Carbohydrates. Where does carbohydrate come from? Wheat, rice, right, all the kind of burgers, pizza, right, potato, then sugar, after carbohydrates sugar, right. Carbohydrates also come from milk, right. So if I cut the source of carbohydrates, then the source of the energy that the cancer cells or other cells require has been stopped. So what can be the other sources? How about I use all the vegetables instead, alright, all the fruits instead. Of course, this vegetables has some amount of carbs, fruits has some amount of carbs, but lot of fibers, alright. So cutting the carbohydrate as a source of energy can be one way of not providing enough energy to the cells, right. Then the cells start consuming the fat cells. So fat cells would be dissolved, and that is a way, if you understand ketosis, how it works. But coming to cancer, so the point is it requires energy like any other cell, right. So along with energy, what else it requires? It requires blood flow, and energy to the cell will come through the blood, right. So the blood should flow, and the nutrients will diffuse through the blood to that cell, isn't it. So for flowing the blood, there should be a creation of vessels towards the cancerous tissue. This creation of vessels is called angiogenesis, alright. Now let me show you on the screen how the cancer tissue looks like, and how it is covered with the extracellular matrix, and how the vessels form, alright. So if you see the slide, so assume that this is a cell, this is a tissue. Okay. Tissue is composition of lot of cells. This tissue is covered with lot of what you call, is covered with extracellular matrix. This is a cancer tissue. All right. Now, what will happen is, to provide the energy to the tissue, there is formation of vessels, right, V1, V2, through which the nutrition will flow, and then these vessels will be further divided into capillaries, like that, right. So, through which the nutrition will flow. So, I will just remove the extracellular matrix, so not to confuse you with the other things. Okay. All right. Just let me quickly draw it again. This is a cell, and then formation of vessels, right, and then from vessels there are a lot of capillaries, right. Same thing happens on other vessel 2 and then vessel 3 and so on. These vessels will carry the blood, right. This vessels is carrying the blood. Through this will diffuse into capillaries, and it will reach to the each cell within the cancerous tissue. The nutritions through these vessels will reach to the cell in the cancerous tissue, and thus helping the cells to grow further, thus helping the tissues to grow further. All right. What we want to know is, can we use a drug or a combination of two drugs to stop formation of these vessels? If I stop the formation of this vessel, what will happen? If I stop the formation of this vessel, what will happen? That the nutrition reaching to the tumor will reduce, isn't it? How can I design a microfluidic platform? To study such a effect. So, for that, if you see this particular schematic, you can see that this is a representative of a vessel, the red one. This is cancer, this is ECM matrix. All right. Now, what will happen? That the blood will flow through this, and it will diffuse into the tumor, right. That is what we have discussed. So, how this microfluidic platform will help us to understand which drug is called anti-angiogenesis drug, which anti-angiogenesis drugs or combination of it will stop the formation of vessels, right. To study that, we will be using a microfluidic platform such that it has two channels. Here is channel 1, here there is channel 2, channel 1, channel 2, in between there is a matrigel, you see here also, this is channel 1, this is channel 2, and in between this region there is a matrigel. Okay. So, now what will happen, that in channel 1 we will load cancer cells, in channel 2 we will load endothelial cells. What are endothelial cells? Endothelial cells are the cells which helps to form the vessels, that will carry the blood, this cells. All right. So, now I will, and then I will flow the media on these endothelial cells, and I will just load the cancer cells with media, I will not flow it, right, because the flow of the blood occurs in the vessels, not the there is extracellular matrix which provides the nutrition, this media will provide the nutrition, but it is in a stable condition, we are not flowing it, it is stagnant, alright. So, what I said is that in the channel 1 there will be media, but not flowing, media but not flowing. Channel 2 there is a flow of media. Media is a solution to keep the cells alive, media is a solution which have all the nutritions to keep the cells intact. Okay. In between what is there? Matrigel is there. Now, I will see how there is a formation of channels because of release of cytokines. There is a formation of some blood vessels from channel 2 towards channel 1 like this. When I flow it for 48 hours, I will see that there is a channel formation from channel 2 towards channel 1. Okay. I want to stop the formation of these vessels. For that, what can I do? I will treat my cancer cells in channel 1 with drug 1 and again see how these vessels are forming from channel 2 to channel 1. Then I will treat the cells in the cancer cells with drug 2. Again I study the formation of the channels. Then I treat the cancer cell with drug 1 plus drug 2 and I will again check the formation of channels from channel number 2 to channel number 1, formation of vessels from channel number 2 to channel number 1. What I will find is that a drug which is effective or a combination of the drug which is effective will stop formation of channels or the channels would be broken like this. If the channels are broken or the channels are not forming, then the nutrition from the blood cannot reach to the cancer because there is no channel carrying the nutrients. Got it? So, the idea is how to design this microfluidic system, and this microfluidic system would be a platform to understand a combination of different drugs. Alright. So, we will study how to fabricate this in the class. I will go to the next platform. Now, this is a flexible MEMS sensor and this is to understand the electrical and mechanical properties of tissue. Alright. How? You see what is there here? If I see there is this ohm shape sensors are there, right, 1, 2, 3, 4, 5, 6, 7 and 8 sensors are there, right, and if I zoom one of that it looks like ohm, but in another way it also looks like a resistor, right. So, what is it? It is a strain gauge, it is a strain gauge. That means, if I apply a pressure on this particular platform, then there will be change in the strain and it is a piezoresistive strain gauge. So, there will be change in the resistance in the strain gauge, resistance of the strain gauge would change. So, if I put a tissue in the center of this particular chip, and if I apply a force, then there will be change in the resistance of the strain gauges, right, depending on the elasticity of the tissue. Okay. Second thing, on this strain gauge, on the area of this strain gauges, we have an insulating material over which there are gold pads. These are the gold pads 1, 2, 3, 4, 5, 6, 7, 8. And I zoom one gold pad, what do I find? I find that the gold pad looks like this. Why? Because below gold pad there is an insulating material. What is that insulating material? Insulating material is my silicon dioxide, right. So, silicon dioxide is used as an insulating material and we have a strain gauge on the bottom. So, it is like a strain gauge insulating material, on that you have the gold pads, this guy, alright. Now, on this gold pad I will fabricate some pillars like this, pillars, okay, and I will perform a process called lift off technique to coat these pillars with a metal. Now, when I place the tissue on these pillars, what will happen that if I place the tissue on these pillars, right, like this, and if I apply a force. So, let us say I have a tool which looks like this and it has the gold pad, right. This one is a gold pad and there is some connection to this gold pad, alright. So, there is a connecting wire, this is the indenter, alright. What will happen if I apply a force with this indenter onto the tissue, that amount of force that I am applying here, right, the amount of force that the sensor will experience is based on the elasticity of the tissue or stiffness of the tissue, right. If I apply a force through this indenter, right, this one, if I apply a force to this indenter onto the tissue, then the amount of force that the sensor will experience will be based on the stiffness of the tissue. Second point is, if I apply a voltage, you see there is a gold pad, right. So, apply a voltage, let us say V2, this is V1, voltage between V1 and V2 or pad 1 and pad 2, then depending on the resistance of this tissue, I will see different change in current. You got it? If I apply a voltage between the top pad and the bottom pad, that the top one is on the indenter, the bottom one is on the chip, right, and if I apply a voltage between two pads, I would be able to see the change in resistance of the tissue. Thus, you can measure the electrical property, which is the resistance, and mechanical property, which is the stiffness of the tissue, with the help of this particular chip. So, there is a mechanical sensor and then there is a electrical sensor, both are integrated on a single chip, and this chip can be used to measure the change in this electromechanical properties from onset to the disease progression. Since it is made up of flexible material, that is why we can bend it, and then I will show it to you after we fabricate this sensor, how to use it for your experiments. Okay. Let me move to the next part of the sensor, and this is on the immunotherapy, a microfluidic chip for understanding the efficacy of immunotherapy drugs. Microfluidic chip for understanding the efficacy of the immunotherapy drugs. All right. So, the idea here is that if there are 3 drugs I2, IT1, IT2 and IT3. These are immunotherapy drug 1, immunotherapy drug 2, immunotherapy drug 3. For a given, there are patient 1, patient 2, okay. There are 2 patients. We have to give which drug out of 3 to patient 1 and to patient 2. How we will design? How we will know that patient 1 out of 3 which drug would be more effective, which drug has more efficacy, right. Same thing goes for patient 2. So, you have to design a patient centric platform that can help the doctor to identify which drug to subscribe, or which drug patient 1 should be given, which drug patient 2 should be given out of given or available drugs in the market. We will discuss about immunotherapy later on. So, one way of doing it is using a transwell. So, in the transwell I will take the cells from the patient, I will take the cells from the patient and then I will grow the spheroid. So, I will take the cells, I will put in a U bottom plate, and after a while I will see that the U bottom plate will have this clumped spheroids, it is called spheroids, alright. So, this spheroids I will load here in the, this is your transwell, alright. Then I will take the T cells, I will extract T cells from blood of the patient, that is a patient 1, and I load T cells here. Now, these filters are such that the T cells cannot go through this filter, and these cancer cells or spheroids are covered with matrigel. So, now what we have here? We have cancer spheroids plus matrigel. Here we have T cells, right. Now, because of the release of cytokines, so in T cells consist of, when you say T cells these are white blood cells in a way, and the basic 3 classification can be T regulatory cells, CD4 cells, CD8 cells. CD4 cells are also called helper cells, CD8 cells are also called killer cells, alright. So, when we keep the T cells over the cancer spheroids which are covered with matrigel, then after 48 hours if we take out the T cells and perform flow cytometry analysis, flow cytometry analysis, what we will find is that the CD4 CD8 ratio is different, CD4 CD8 ratio is different. Now, similarly I take 3 different transwells, right, and there is this transwell looks like this, and I load the spheroids with matrigel. If there are 3, we should keep it uniform, and then there are cells here which are your T cells, T cells, T cells. These T cells are treated with immunotherapy drug 1. These T cells are treated with immunotherapy drug 2. These T cells are treated with immunotherapy drug 3. Okay. Now, after 48 hours, when I take out T cells from here and I measure CD4 CD8 concentration or and then plot it in a ratio, same thing I will do for here and same thing I will do it for here. What will happen that the drug which is more effective, there will be more number of killer cells. The drug which is more effective will have more number of CD8 cells. So, from this platform we can select which immunotherapy drug will work for our patient 1, right. So, this can be used as a patient centric platform. What is the difficulty in this? The difficulty that you can see here is that each of this is a static platform. All 3 of this is a static platform. What we require? We require dynamic platform. Why we require dynamic platform? Because our body is dynamic, and that is why you require a microfluidic chip for understanding the immunotherapy drugs, efficacy of the immunotherapy drugs, right, and in a way that we can run in the dynamic platform, which is your microfluidic chip, right. So, we will see how we can design this microfluidic chip as a part of the course, and I will stop here discussion about this 2 different sensors, because I feel that you have a smaller modules, it will be easier for you to understand a lot of new terms that came to you that suddenly you have learned in this particular module, like angiogenesis, right, vessel formation, endothelial cells, cancer cells, matrix gel, extracellular matrix, right, efficacy of a drug, screening of the drug, flow cytometry, microfluidic chip. So many things that you have learned in this last few minutes. So, first digest those stuff, understand, Google it, that what exactly each meaning means. Efficacy, what does it mean, right, flow cytometry, how does it work. So, lot of things that I say, you have to catch up the words and go and see in detail each experiment, because I cannot cover everything in the in this particular course, because that itself is the part of a different course, alright. So, I will stop here, and the only idea that I wanted to show is that you can design a microfluidic platform to study how to use this immunotherapy drug. So, let me just show you to this platform, and then we will stop the lecture. If you can see the screen, this microfluidic platform that we can see over here, right, there are 2 channels, channel 1 and channel 2. Channel 1 and channel 2, we can flow. So, this both the channels are merging at a point like here, right, both channels are merging. So, what we can do is we can first take the spheroids and load spheroids in the central region, alright. Now, there are some spacers here, and then we will flow the T cells and this and this, and then with the help of the peristatic pump we can do this flow for 48 hours. Right. There is an inlet and there is a outlet. So, if you connect the inlet with outlet, after flow it will come back and again it will flow. So, when you allow it for 48 hours, after 48 hours you can check the CD4 CD8 concentration, alright, and then you treat the drug T cells with immunotherapy drug 1, and again flow it for 48 hours, understand the change in the CD4 CD8, drug 2 again 48 hours, see the change in CD4 CD8, drug 3 again 48 hours, see the change in CD4 CD8, and the one with the CD8 is higher, you use that drug as a patient centric platform. This is just an idea of using a microfluidic chip as a dynamic system or a dynamic platform compared to the existing transwell, alright. And then we will talk about what is PD1, what is PDL1, right, when we actually see how we can fabricate this particular chip in our process. Alright. So, it is a immuno checkpoints. I will discuss in detail what is PD1, PDL1, how the cancer cell looks like. That is a part of the separate study, but since we are understanding the immunotherapy drug and the testy immunotherapy drug, we need to understand how the what are different terminologies that are used in this particular research area. Alright. So, here I will stop my class. In the next class we will see a very interesting problem called electronic, or not actually a problem, a technology that people are working, which is the electronic nose, to identify a very important problem, which is a non-invasive way of detecting a disease. Can we design a system that can help us to identify the disease just from understanding the breath signature? Whatever I am exhaling, from that my exhale breath can I identify a particular disease, right. So, we will see how the sensors for that particular application can be fabricated. We will see in this class, but why it is important to do that analysis, we will see in the next module. Alright. Till then, you take care. Any questions, free to ask in the forum, and I will see you in the next module. Till that, you take care. Bye.